The next one I want to introduce, that is, he's already standing here, Thijs. I'm really proud that he's presenting here. I saw a session from him at Objective-SC. It was very interesting. If you don't saw it yet, please look at that one. He has also had an interview on Mac admins. I don't know what version. But anyways, he is an award winner security resourcer. And you know what? I will let him introduce himself. So here's Thijs Alkemade.
Thank you. Thank you for the introduction. I'm also going to talk about packaging, but from a completely different point of view, from the security point of view, and how to verify that the package is actually valid. But first, a little bit about me. I'm a security researcher at Computest. Computest is a security company in Zoetermeer. We do stuff like pen testing, we have a managed SOC, we do incident response. But me, together with two other colleagues, are the research team, which means that we don't do work for customers, but instead we just do research that we hope can make the world a little bit safer. So other work that you may have seen from us or that you can check out is a zero-click RCE vulnerability in Zoom that we showed at Pwn2Own in 2021. We won Pwn2Own Miami last year, which is a competition centered around finding vulnerabilities in ICS software. And there's the Black Hat USA and DEF CON talk. It is also the same one, or pretty similar to the one given at Objective by the Sea, about the process injection vulnerability. And we just do this research to help make the world a bit safer, to solve these vulnerabilities, but also to talk about them and to help improve the knowledge about these vulnerabilities. Also giving presentations like this to really help people understand, well, how do you find these vulnerabilities and what can you do when you find them? Now, why do I look at macOS? So there's a lot of subjects that I've looked at over the years, but macOS has always been kind of a specialty for me. I once, a long time ago, was a developer on Adium. I've used Macs all of my life. So it's basically like whenever I'm stuck on a project, I'm using a Mac anyway. I just look at what processes are running. I think, well, maybe there's something in that one. And I just start looking at it, see if I can find a vulnerability. So it's kind of like just, yeah, I'm bored with the current project. I want to look at something else. And this is the thing closest at hand. So I start looking at that. So that's basically how most of these projects start. Now, what is the plan for today? I'm going to talk a little bit about the format that's used for PKG files that you're probably all familiar with, but maybe not all of the technical details about what's in there. And I'm going to explain the vulnerability I found, CV 2022-42841. I reported this to Apple, and it was fixed in the macOS Ventura 13.1 release, which is, I think, from December or November, somewhere around there. And then I will demonstrate how that vulnerability could be applied to bypass mitigations like gatekeeper and system integrity protection. So first, a little bit about the PKG format, which is basically just a XAR file. So PKG files are XAR files with certain predefined file names like PKG info that are automatically read. XAR is a file format for both compression and for archiving, just like zip. So you can both compress and combine multiple files. And there's basically three parts in a XAR file. You have a header of a fixed size, followed by the table of contents, so the list of files within the archive. And then there's something that XAR calls the heap. And the majority of the file will be the heap. That's really where the data of the archive is placed. Now, the header is typically 28 bytes, and it includes a couple of fields. It's pretty small relatively compared to the rest of the archive. Basically, it just defines what's important here is the hashing algorithm that will be used for the entire file, and also some information about where to find the table of contents. Now, the table of contents, that one's more interesting. This is a compressed XML document. It starts with some general information about the package, like the checksum of the file itself, when it was created, stuff like that. And for each of the files within the archive, there will be an entry in this XML document. I'll have an example later to demonstrate that. And then the third part, that's the heap. And that's the actual data of the files within the archive. So that will be placed somewhere on the heap. And if you're familiar with programming, this has nothing to do with a heap like in a C program where you can allocate stuff on the heap. It's just randomly addressable data. That's why it's called a heap, but it's not really related to that any more than that. So as an example of a file, this is readable. This could be an example of a file within a package file. And this one is called package info. I think that's a file that's always required to be there. As you can see, it defines the name. It defines where that file is placed on the heap. So it says the offset where that file is on the heap. So it starts counting from the first byte of the heap and then goes to that offset. And then the length of the data on the heap. And there's also an encoding. So in this case, this file is bzip2 compressed. And there are these checksums. So both the compressed and the non-compressed checksum are included here. And as you can see, there's also a different size. Size is different than length. Size is after decompression. So each entry in this XML document refers to where that file can be found on the heap. And that's a pretty flexible format because that means that you can use it means that if you have two files that basically have the same contents, that you can refer to the same place on the heap. So if you just put both of them on the same place and then you refer to that location, then you can just use one place for that file instead of including it multiple times. You can even make them partially overlap, like if you have a file that is a prefix of another file, and you just refer to only that prefix part for the one file and the entire part for the other file. So there's a lot of flexibility for how you can include files within such an XAR archive. Now, XAR archives always include integrity checks using hashes, even if they are not signed. And therefore, the hash is always for each file, the hash is always included in the table of contents. So in the header, a hashing algorithm is defined. So in most cases that I've seen so far, that's still SHA-1, even though it's known to be broken. I don't know why that's still used, but it is. And then also the hash of the entire table of contents, that's also included. But that's not within the table of contents, because that would be a cyclic dependency, because then the hash would depend on itself. So instead, that hash is placed on the heap. So to visualize that, so we have the header, we have then the table of contents, and then the heap. Typically at the first offset, so at location 0, there will be the hash of the table of contents. So whenever you have a XAR file, you can check very well whether or not it's corrupted or whether anything has gone wrong with it. If you use it for like long-term storage of data, then you have all of these integrity checks. That means that if anything had happened to the file, you can tell based on either the hash of the table of contents or the hash of the file. You can even extract the other files even if one of the files has gone corrupted. So it's pretty well designed to be safe even if your archive gets corrupted in the future. Now, how about package files? Those can also be signed, and signed is really something different than just the integrity checks here. So the integrity, that's for accidental modification to the archive, so some bits being flipped somewhere. But the authenticity of the file can also be guaranteed using a certificate. So just like you can use a certificate to code sign an application, you can sign a package file. And that's just based on how XAR files are signed. That's basically the same thing here. Now, the way that works is similar to the hashing of the table of contents. The certificates are in the table of contents, but the signature itself is placed on the heap, because that would also be a cyclic dependency. You cannot put that in the table of contents. So you end up with this kind of layout. There's the table of contents, then followed by the table of contents hash, and then the signatures for the table of contents hash. So the signatures are generated using that hash, which then guarantees the integrity of all of the files. So this is how you would verify that a XAR file is correctly signed. You first use that same hashing algorithm to hash the table of contents, compare that to the value you've read on the heap, and then you verify that table of contents hash with the certificates that you also obtained from that table of contents. And if you want to verify a single file from that archive, then you need to extract it, hash the file using that hashing algorithm, and then compare the hash with the computed hash that you found in the table of contents. There's some pretty interesting properties that this method has, because you can just extract a single file from the archive and verify that it is not modified and that it's still correct without reading the entire archive. So what you often see is that you can download a zip file and then you hash the zip file and you compare that hash. Now that's also a way of verifying that that zip file is correct. But in that case, you really need to read the entire zip file and only then can you compare the hash. But in this case, if you have a XAR file, you can just take one file out of it and verify that that one is correct. You don't need to read the entire archive. Maybe you don't even need to download the entire archive. I think there's some stuff in Apple's software update part that maybe doesn't even need to download the entire thing before it starts processing the files. And then there's also an interesting feature here that you can add more data to a XAR file because it's on the heap and there's no files referring to it. It will not invalidate the signature. So if you have a package file and you put whatever trash you want after it, it will still be valid and it will still show up as properly signed, even without this vulnerability that works like that. So the vulnerability that I found. Now, as I just said, the table of contents hash is used in two different ways. First, it is used to verify that the data in the table of contents is still correct, that there's no bit flips in there, that there's nothing being modified. And the second check is for verifying the signature. So basically two different places where the table of contents hash needs to be checked. But what happens if those use a different value? That's something I wondered. And then I was looking at the code because libxar is open source. It's one of the packages Apple publishes as open source. And I noticed this, when you open a XAR file, then this is the code that runs. So this obtains an attribute from the XML, looks for the checksum offset field, and then reads that into an integer. So here it defines it as an unsigned 64-bit integer offset. And it will obtain that from the archive. Now for the code that would verify the signature, this was the code. It would also go look at the checksum offset attribute of the XML document and then read it and use it later to read from the heap. But as you can see, what I've highlighted here is that they now use a 32-bit integer for reading that offset value. And that means that it's being cast into a smaller integer. So it started in the one place they use a 64-bit integer, so it can be pretty large value. And then here it's just the lowest 32 bits are being kept of that value. So if you would take, for example, an offset value of 2 to the power 32, that's not possible to represent with a 32-bit integer because it's too large. Then the integrity check would first read it from the first address, so the same value as I specified it. But then the signature check, because it would ignore all of the highest bits here, it would read it from address 0 on the heap. So at this point, there are two different values being used as the hash for the signature verification and the integrity check. And it could contain different values. Now, what does that address mean if you translate it to a file size? Well, 4 gigabytes. I mean, that may sound a bit large for a package file, but it's also not that large that you cannot just download it within a few minutes. Nowadays, that really isn't that much. Your macOS updates are larger than 4 gigabytes, yes. So what can you do? So you can start with a signed package file, and then it has the original table of contents hash, and you keep it at offset 0. But then you add some more padding to the heap, which you can do because it does not invalidate the signature. And then at the address 2 to the power 32, we place a new signature. So the one used for the integrity check is the bottom one, so the one at the end. But the one used for the signature verification is the top one, so the one just after the table of contents. So to go into more detail about how to do that, you take a validly signed XAR file, just any existing package file. You read the table of contents, you parse it, you do the XML stuff that you need to do. And you make any changes that you want. Just add a new malicious pre-install script or something like that. And compute the new table of contents hash, also change the hash offset to 2 to the power 32, so the check will use the correct value. Then generate a new compressed table of contents, compute the hash, and put that value there. Add some more padding to make sure that the file is actually to the 32 bytes, and just place that new table of contents hash there. Now, whenever anything Apple used would verify this file, it would just show up as being correctly signed, still by the same person or the same certificate that signed the other file. But I could just make any arbitrary modifications to that file. Anything I wanted, I could include in the file. Now, I didn't really want to figure out how to actually package files, so I just added a malicious pre-install script, so anything it would just automatically run that pre-install script instead of having to copy files or stuff around. And then when the installation would start, it would run that malicious command. And I even found a way to avoid making something suspiciously large, like a 4 GB download. So if the user has to wait like 5 minutes, then they may see, well, I'm really not on the correct page for downloading this file. There might be something wrong here. So instead, you can just paste that file on a compressed DMG file. Really not weird to first download the DMG file and then install a package. And then, because the padding can just be anything, it compresses really well, so you can just, the end result is a package file or DMG file of less than a megabyte. And then it contains a 4 GB package file because it's compressed. So we had this vulnerability, and now really the question was, what can we do with this? What is the impact of this? Well, and it turned out to be applicable in quite a few ways. So first of all, there's Gatekeeper. Now, Gatekeeper means that if you download an application from the internet, it will do some extra checks compared to when you launch an application normally. And one of the checks is that an application is notarized, which means that it has been submitted to Apple, and that Apple has given it a notarization ticket or something like that. And that also applies for package files. Now, for package files, they just submit the table of contents hash to Apple, and then Apple says this one is notarized, or Apple says this one is not notarized. And as you may have guessed, the table of contents hash that they submitted to Apple was exactly the same one as used for the signature verification. So if you took a properly notarized package, modified it in this way, it would still be counted as notarized. So you would not get a warning like this. And if you download this and try to install it, Gatekeeper would not show any warnings at all. Next up, system integrity protection. Now, if you install a package, then the way it's installed actually changes depending on who signed the package. If a package was signed by Apple, then the installation is performed by system install-d, and everybody else just gets normal install-d. Because one of the security measures in macOS, system integrity protection, means that certain files cannot be read or modified except by specifically signed software or Apple's own software. But there are certain components that still need to be updated in some way. So system install-d is just exempt from all of those system integrity file system protections. So it can just write to any location that is writable on your system. So not your system volume, but anything else can be written to using system install-d. So if you take a package that was signed by Apple, and modify that one, then we can also run code without any of zip's file system restrictions. And what can we do with that? Well, here's some examples. We could give our application all TCC permissions, so we could give us access to the webcam, microphone, whatever, directly without the user giving permission for that. We could read all of the files on the disk, even those protected in like a data vault, like the mail database, which you can normally not read. We could load a signed kernel extension without the user having to approve it, at least on Intel Macs. I don't think that works on M1 Macs. And also a fun one, we could persist in locations that would still be protected by system integrity protection, which means that like your third-party antivirus solution would not be able to delete the malware, but Apple itself would need to intervene and delete it from the computer. So they would need to push out an update and delete that malware from the computer. So if you combine all of that, then you would have a very interesting attack vector for infecting users with malware, because the user downloads a package, gets absolutely no warnings from Gatekeeper at all. Even if they inspect the package, even if they know how to check the certificate, they would see a valid certificate. A user performs the installation and they get full access to their computer. And the malware may even persist in difficult to remove locations. A video of that. I hope that works here to demonstrate it. First, to demonstrate that it's macOS 13.0.1. We download this one from the internet. As you can see, it's only 300 kilobytes because of the compression. But the file itself is actually 4 gigabytes in size. And if you inspect it, it's just signed by Apple. It's just an Apple software update. It's my demo user in a VM. I don't know why my password is. So it says the installation failed, but actually that's because it's only running a pre-install script. And it's now writing a file into the system policy configuration directory, which is the directory where Apple keeps the list of approved kernel extensions, where you can see the kext policy file there. So it's really a location where third-party software should not be able to write or read from at all. But with just installing one package, we can put a file there. Now, I also looked at if I could get privilege escalation, so for a normal user to a root user. It's not really necessary in this case because the user enters their password, but that's not really a vulnerability, of course. And I looked, but I couldn't really find a way to do it, except if I combined it with like third-party software. So if you have a third-party tool that automatically installs updates in the background, then that often runs as root, and it often works with package files, but it really depends on the software. So for example, I know Zoom nowadays has a privileged updater that runs in the background, and when there's a new update, it's automatically installed. But if you combine it with something like that, then you could get privilege escalation. And in fact, this vulnerability was originally found when I was attending this presentation from Patrick Wardle at DEF CON, where he talked about the vulnerability in the privilege updater by Zoom. And I was looking at their fix and I was thinking this cannot be the best way to do it. And it turned out that that was the best way to do it. It's just that the XAR API is really weird. And that's why they ended up with this, when I ended up discovering this vulnerability. Something you may also be wondering, the system updates of macOS itself was not vulnerable to this. They were using the correct table of contents hash to check if a file was correct. Because otherwise it would have been a nice RCE vulnerability. Because if you send up a content caching server, you can just serve updates out to other users on the network. And that doesn't work with this. It doesn't accept them. Spent a lot of time trying to get this to work, but it didn't, was not affected by this vulnerability. Sadly for me, but I guess thankfully for everybody else using macOS. So the fix, well, surprisingly, the entire fix is changing 2 characters. changing OINT 32 to OINT 64. That's all that's changed in this for fixing this vulnerability. And because it's open source, you can actually see it on GitHub like this when they publish the new version of the code, that they only changed this part. Now, that does address the vulnerability, but I do feel like it would be better to make some changes to the library to make this vulnerability harder to reintroduce in the future. Because there has been a similar vulnerability back in 2010. So 13 years ago, they had a vulnerability almost the same as this one. But at that time, they were using like offset 0 always for the TOC hash in one place, and they were reading it from the archive in another place. So it's really similar to a 13-year-old vulnerability, which I think is something I haven't seen before. And it would be quite easy to fix this, like in general, just save the table of contents hash somewhere in memory while the file is open, and it would just be impossible to reintroduce this vulnerability in the future. Now, that's all I have for you today. But we do have a full write-up of this vulnerability if you want to have more of the details, or if you want to see the video again or something like that. You can find it on our website, or you can follow us if you want to learn more about the stuff we find. There's still some interesting Apple vulnerabilities coming up later that we still cannot talk about, but at some point. Any questions?
You know if this fix was backported to the security updates for Monterey and Big Sur?
So the question is, do I know if this fix was backported to Monterey and Big Sur? I don't know for sure, but I think so. It's such a trivial fix that I can't see a reason why they wouldn't backport it. But I haven't checked the release notes to make sure. Any other questions?
Is this the same case as Jemf talked about on the logs, where a hacker was injecting Final Cut Studio, where they added something in the package which was not detectable, and where they followed the hacker for a couple of years?
That was the Final Cut Pro. It was a Chinese, it affected the App Store.
I thought they were that they were also adding.
Yeah, it was injection of some sort, but I think it had to do with like specific apps that was like mimicking the App Store within. So it was like a valid Final Cut Pro package.
Yeah.
But then kind of repackaged, but in China. It was like a third party, but I can't remember. We'd have to take a look.
Because it looks very similar on what he just says about the Xebia out. Because you can add something. But okay, you don't know.
No. I'm also not, sorry, for online, the question was about the Final Cut Pro that was infected with malware. I'm not familiar with that specific case, so I really can't comment. It wasn't me.
No comment.
Any other questions?
I think you are quite clear. Yeah, thank you.
Thank you.